Hello, I'm Michele Cocca and I'm going to present my PhD research titled From Combustion Engine to Electric Vehicles in Free-Floating Car Sharing Systems, a Data-Driven Approach. So, free-floating car sharing is basically a front-end-less car rental model where the user can pick and release the car everywhere within an operative area and interacting with the system just with a web-based application and paying only for the time spent driving. This kind of mobility, shared mobility, can reduce the space lack caused by the private car ownership and thus improving the quality of life in congested urban centers, decreasing the pollution due as well to the private car ownership. The main research question in my work is, it is possible to move from combustion engine to electric vehicle fleets keeping the free-floating paradigm? In other words, it means, can I avoid to force the user to plug the car to a charging station at the end of each ride? The main contribution that my work carries is, first of all, an open source software able to download real free-floating car sharing data and an open source electric car sharing simulator. And finally, a proposal of standard methodology to study the electrification of shared mobility. So the first step consists into a scraper able to get from real car sharing provider data, standardize them in order to get the story of each car in terms of rentals, real user ride, and a further module able to perform some characterization on those data. Then I developed a simulator able to replicate the user's habits in a electrification scenario. It takes in input the user's pattern and the electric car sharing system setup and measures the number of infeasible trips, namely the trips that the system was not able to fulfill due to completely battery can run out. Then the simulators adds other user's discomfort metrics related to the car plugging operation. On the first work, I studied how many charging stations should be placed in order to have zero infeasible trips. Initially, I divided the target city, Berlin in this case, in squares. For each square, I computed a likelihood which reflects the user's driving pattern in that area. In the left figure, the likelihood is the average parking time, while in the right one is the absolute number of parking. Keep in mind that the more the area is red, the more the likelihood is higher. Then I simulated the user's driving patterns, equipping with a charging station the top n zones for each likelihood, increasing n until the number of infeasible trips is equal to 0. The likelihood corresponding to the number of parking reaches 0 infeasible trips with less charging station than the other one. Once identified the minimum number of charging stations to reach 0 infeasible trips, I studied if it was possible to still improve the charging station placement. I ran several optimization algorithms which discovered some areas having an hidden energy demand, at least in Turin, mainly characterized with a high residential density. Covering those areas with a charging station, I was able to still reduce the number of charging stations to guarantee zero infeasible trips. Finally, I performed some temporal and socio-economic correlation with the car sharing demand. In particular, the random forest regression plot on the left well predicts the number of rentals for the next hour with an expanding window approach. The right plot shows instead the mean average percentage error in the prediction of number of rides leaving a given neighbor in a given time being. In particular, the plot shows how the number of socioeconomic features impact the map, thus validating the presence of a correlation between city shape and users' car sharing demand. So then the future work will be study the relocation impact in electric car sharing system and how those electric car sharing system can scale.